All right, I thought it might be an idea just to do a bit of a recap on all the work that we've covered so far. It is a lot of work, but let's just have a look. So one of the things that we've looked at in terms of enolate chemistry, we've been focusing a lot on just alkylating reagents. So this is the type of the electrophile that we have been using, some sort of leaving group on it, an X on a carbon, and it could be primary, secondary, or tertiary. It might also be next door to, activated by being on an allyl group, or it might be next to a ketone or a carbonyl that activates it a bit more. But they've all been a leaving group that's sitting on a carbon with an X on it. So we've covered quite a few of those. We've also had quite a good look at all the different types of bases that are common in this chemistry, and so there's been quite a lot. I gave one very specific video lecture where we covered all the main bases with that, and so you do need to get the hang of that. And then what we've been really looking at the moment, just as we've finished off pretty much, is in terms of the alkylating agents, we've been looking at the flavors of the carbonyl group itself in terms of this alkylation, and so of that we covered the esters and the carboxylic acids, and then we also had a look at aldehydes. Now the aldehydes were the first functional group that came up with a bit of a problem in the sense that aldehydes themselves are also very good electrophiles. We're going to come back to that now. So the aldehyde, we had this problem, and there were three solutions to this problem. The first was the enamine. The second was the aza-enolate. And then the third was the silyl, silyl enol ether. All right. The silyl enol ether was itself actually not just only a solution to the aldehyde problem, but something that could be used in a whole lot of other enolate chemistry, particularly for reacting with sterically hindered alkylating agents. So it wasn't just with aldehydes, but also with the other flavor of the carbonyl group, and that is the ketone. So ketones themselves, we can use silyl enol ethers to form the silyl enol from ketones and then react them at a later stage. So that's very common, and indeed we can use them with esters as well. So this is quite a broad feature. But ketones, they had another problem. Just like aldehydes had a problem in terms of self-condensation, ketones also have a similar problem. The problem is regioselectivity, and so what we ended up discussing over here is that because the ketone could be deprotonated on either side, or possibly on either side of it, it gave rise to this idea of having either the kinetic or the thermodynamic enolates. So this is quite a bit of work here. The kinetic enolates we've looked at. They are generated under very cold conditions with strong bulky bases and its non-equilibrium conditions. The thermodynamic enolates, these are generated with I say not high temperatures, because it could be at room temperature, but temperatures higher than say 20 degrees, equilibrium conditions, and using fairly mild bases. And then the last flavor of the carbonyl that came in was the 1,3-dicarbonyl compounds, and we looked at those and how they can actually undergo, if there's an ester part to it, they can undergo decarboxylation. So these are all the ones we looked at. Okay, so this constitutes a hell of a lot of work, and it's a lot of the foundational work that we need to cover. But where we're going from here is we have really, for all intents and purposes, you're not going to see anything different now. We have totally covered all the bases. We have totally covered the different flavors of the carbonyl compounds. Maybe amide isn't mentioned here, but we can stick it there, but you don't often use amides in these chemistry, and if they do come up, their reactivity is the same as if you have an ester or acid there. It's nothing odd with that. So we've covered a lot of there. Everything else is going to be revolving around the different types of electrophile, and with that there are another two large classes of electrophiles that we're going to be looking at. The one is the aldehyde and ketone class. All right. So both aldehydes and ketones can act as electrophiles, and so we're going to be looking at that under the guise of aldol reactions. The carbonyl itself, in the form of an ester, is also something which you're going to be coming across, and so something like that. This comes under the Claisen type reactions, and so these are all these carbonyl type things, and then the last one is the conjugate addition, and this is to compounds that look something like that. They're still going to have a carbonyl group on them, and but the way that they act as electrophiles is slightly different, and that's a whole section as well. But the chemistry, all the kind of mechanisms have been already covered over here. So there's a lot of work that's been done. It's now just knowing all this, we're now just going to be applying it to a different electrophile, and that's what we're going to be studying